Hello, everyone. Welcome back. So today we'll learn about the substitution method. It's a different way of integrating functions, especially when the integral we have is it's maybe clear how to integrate it by hand. So our goal is first of all understand what's called the substitution rule and when it can and cannot be used. And then we'll also talk about the substitution method and use it to evaluate both indefinite and definite integrals. So as it says, sometimes when it helps to actually integrate and some integral helps to actually write in a way that it's easier to integrate. Okay, that makes sense. Now the question is how and when can we do that? So let's look at an example to kind of get us started. Let's come over here. Okay, so how about we have this? Let's say we just have an indefinite integral cosine of 2x plus 5 dx. Okay, that's our integral. Now we know what the integral of cosine is. We also know what the integral of 2x plus 5 is. But now we have a function here together, and this one, it might be as clear how we go backwards. Okay, because we know we integrate this, integrate cosine, we get something involving sine, we're not sure what else, what else to put with it, what else it needs to be accurate. And of course, you could go through a trial and error process to find that, but there's a better way. Let's look at what's called the substitution rule over here on the left and kind of see how this works. And then I can explain how to use it. So first, talk about an indefinite integral. It says, and this solves something's called the u substitution method because someone a long time ago picked the variable u to use instead of x for the substitution. That kind of stuff. But you can use any variable you want. Okay, so what we're going to do then is let's say a function, or we're integrating a function like this, where it's basically is a product of two functions. Okay, and basically, if you remember from algebra, this is called a compound function. So within a function f, you have another function g, and it's basically multiplied by the derivative of this interior function g. Okay. Now that's kind of mathematical, but as we'll see, what the way to think about this is think of it as if we have a function on the inside of our integral, we have a function, and it's basically multiplied by its derivative. And this derivative can be off by a constant, but that's it. It can't be off by any powers of x, just can be off by a constant. We can do this. Okay, that's the substitution rule. I can write this as the integral of f of u du, okay? And basically, that just gives me just an integral in u, which I can then evaluate. I shouldn't have any x's left if I do this correctly, if it's in this form. It's got to be in that form. So we'll show an example of this one where this works, and also show you a slightly different example where this wouldn't work. So you kind of get an idea for how to tell. Okay, so let's take a look at this one. All right, so what we're going to do is, and kind of show you how you got this started with this, and we'll talk about the method here in a minute. So we're going to let, this would be a lot easier if we just simply had like the cosine of x, okay? So instead of using x, we're going to use u. So we're going to say let u equal 2x plus 5, what this is right here, okay? So when you see we substitute that in, that's going to give us just the cosine of x, but we want to make sure we don't have any x's left, so we'll explain that. Now, we're going to take the derivative of this, so we want to find what's called the differential. Remember, du is called a differential, and this is just like taking the derivative of this, okay? This is u, then du, okay? Then we take the derivative of this, okay? So the derivative of 2x is just x, or just 2 rather, and then the derivative of 5 is 0. That's a constant. But how are we thinking about the chain rule? Okay. And also, this is something we take this, find this differential. We're going to have a dx here. If you think about what's the derivative of x, that's going to be essentially dx. Okay, so we're doing the differential. Just essentially take the derivative of this, use the chain rule. So the derivative of 2x is 2, and the derivative of x is dx. Okay. Now, we have these two things we're going to do now is substitute these in. All right. Now, also, one more thing to notice now, what we want to do is replace the terms with x's in our original integral, okay? So that we don't have any x's left, all right? Now, if you notice right here, we have dx. So I'm going to note over here that then dx is going to be equal to, just divide divide through by the 2, that's going to be du over 2. Okay. Now, we're going to substitute in these things. U equals 2x plus 5, and dx equals du over 2. Okay. So this is going to go, not that. So the u is going to go right here. And this du over 2 is going to go right here. And then that's going to give us then this cosine of u, and then replace dx with du over 2. Okay. Now, one more thing. Let's just do something to make this look a little bit better. This is the same as 1/2. Let's pull that out front. Remember, we can do it with a constant. This is going to become 1/2. Since this over 2 is the same thing as 1/2 out front, the cosine of u du. Okay. Now, notice now we just have an integral. We have no x's. Okay. Just u's. And that's what we want. Okay. We don't want any x's left. We have an x left. Either we did something wrong, or this is an example where we can't actually use this method. And sometimes you can't use this method. It just depends. Okay. And we'll kind of, as we'll do some more examples, we're going to see how that works. Okay. Now, we know to integrate this. This is 1/2. The integral of cosine, of course, is just sine. So sine of u. And then, of course, this is definitely variable plus c. Now, the last step I want to do then is just substitute back. Okay. So we'll put it back in terms of x, the original function. And u was 2x plus 5. And so this is going to be 1/2 times the sine of 2x plus 5 plus c. And also something you can do on your own is check and make sure you get that if you plug that back in. Okay. So that is the u substitution. Now, for number 2, let's show an example of one where a similar one where it actually wouldn't work. Let's say try this one. Okay. So very similar. Let's do the cosine of, this time instead of x squared, let's make it x cubed plus 5 dx. Okay. So remember the previous one we had x squared plus 5. This is x cubed. Now, I'll explain why this doesn't work after we get going. Okay. So same thing, we'll let u equal to x cubed plus 5. Okay. And then du in the same way. It's very similar to what we did before. Take the derivative of this. The derivative of this, of course, is 3x squared. And then, of course, the derivative of x is 0. And then the derivative of x, or the differential of x, is dx. So always have to have that dx there, because we have to replace that. And then what this means is that dx, if we solve this for dx, is equal to du over 3x squared. Okay. So once again, we're going to put the u right here, and we're going to put this, replace the dx with that. And what we're going to have then is going to be the cosine of u, which is what we want. But now we have du over 3x squared. Okay, now this is a problem. Okay, we have an x, I'll say x is left. I have a power of x left. Okay, so what this means, so we can't use this method here. Okay, this example. So this is one way to check and see if you try it, you'll find out quickly if you have any x's left. And also double check if this happens, double check everything. Make sure everything correctly at that point. If you have any x's left, this won't work. It has to be entirely integral just with u's. Okay. Now, let's do one more thing with this one. Let's think about how we possibly could modify this to where this would work. So if you notice, the problem is we have this x squared left down here. Okay. Now, so if we need this x squared to cancel out, we need an x squared up here. So let's do a very similar one more time. So once again, we have the cosine of, I'll do x cubed again. X cubed plus 5. But this time it's multiplied by an x squared times dx. Okay, as we'll see, this will actually work. And also make sure it's clear we're not doing the cosine. In fact, we move this, move the x squared front, so it's clear we're not also taking the cosine of x squared as well. So let's put the x squared up here. Squared times cosine dx. Okay. Now, if you notice what happens, and this is where he said basically your derivative of essentially the inside function has to be there except for a constant. The derivative of our inside function is basically, as we saw, 3x squared, which is what we have out here. It can be off by a constant. It can have a different constant or be missing that constant of 3. That's okay. It has to have the same power of x or same power of whatever variable you have. Okay. So once again, let's do this one more time. So let u equals x cubed plus 5. And then once again, just like I did before, this is just the same as our previous example. Du, the derivative of this is 3x squared. Derivative of 5 is 0. Then derivative of x squared is, or x is dx. Okay, and once again, this means, of course, that dx is equal to du over 3x squared. Okay, so once again, we're going to substitute the u in here, and the dx here. We're going to do the substitution method, through that substitution, and that's going to give us then the integral of x squared times the cosine of u, and then du over 3x squared. Now this time, x squareds will cancel out here and here. I can bring this 3 down the bottom as a 1/3 out front. And now we have what we want. Okay, the cosine of u du. All right, and now we have no more x's, which is what we want. Okay, and of course, the derivative of this is very similar to what we saw before. So this is going to be 1/3 times the sine of u plus c. And now finally, just substitute back. And so that's going to be 1/3 times the cosine of x cubed plus 5 plus c. And yeah, okay. So now let's also talk about definite integrals. So as examples, that's the method. And definite integrals work basically the same way, except we also put the bounds, our original bounds, in terms of u. Okay, since we have a relationship between u and x. Okay, and also talk about the method. So what it shows right here, doing exactly the same thing, except now we put the bounds in terms of u as well. Okay, so then we have an integral entirely in terms of u. And since we just get a number out of this, you don't have to plug anything back into, you don't have to substitute back in. So finally, our method, let's take a look at an example. And let's talk about our method then. Let's see which one I want to do. Okay. We'll start over again at 1. Let's say I have the integral from, just go from 0 to 1 of x to the 4th, okay, times x to the 5th minus 4 in parentheses, and this then is raised to the 2nd dx, okay? Let's make it a little more interesting. Instead of the 2nd, let's make it the 3rd or 4th. Doesn't matter. But what I want you to see, let's make it to the 4th power. Now, this is an example where you could actually do this a different way. You could multiply all this out and then, do it one part at a time, which would be correct, but that's obviously be really a pain. So the substitution method is a better way to do it. Okay, so once again, what we're looking for is our outside function is something to the 4th power, which we're going to integrate. The inside function is x to the 5th, okay, function on the inside. So what we need on the outside of that is basically x to the fourth, and then plus, the constant can be off by a constant. We have to have x to the fourth on the outside, which we do. Okay, so if this meant x to the fifth or x to the third, it wouldn't work because this wouldn't be essentially the derivative of what's on the inside except for a constant. Okay, now, so once again, let's let u be equal to x to the fifth minus 4. Okay, then du is going to be equal to the derivative of this, which is 5x to the fourth, and then times dx. In the same way, let's solve for dx. So dx is equal to du over 5x to the fourth. Now, what's different here if we substitute in is thinking about our bounds. Okay, now, when x is 0, I'm going to plug this in. When x is 0, u, essentially this is going to be essentially u of 0, okay, is going to be 0 to the fifth minus 4, and that's going to be negative 4, okay? So our original bound was 0, and u, our bound is negative 4, the lower bound. Then let's do the same thing with the upper bound. X is equal to 1, okay? And then u of 1 is going to be 1 to the fifth minus 4. And then that, of course, is going to be 1 minus 4, which is negative 3. That's our upper bound. Okay? So let's substitute all this in. And so our new integral, in terms of u, now goes from negative 4 to negative 3. Okay? And then we have an x to the fourth times u. Our u was x to the fifth minus 4. Now it's going to be u to the fourth. And then dx, place dx with du over 5x to the fourth. And once again, after this step, all your x's should cancel out, and they do. The x fourth cancels out here and here. Bring the 5, the bottom out front, and that's going to be 1/5 times the integral from negative 4 to negative 3 of u to the fourth du. Okay, and that's it. Now, of course, I still have to integrate it, but that's the idea. And once again, we have no x's left, so this is correct. And this obviously is a much easier function to integrate. Now, one thing you could do is you could actually, once you find this integral in terms of you could substitute back like we did with the indefinite integral, then use your original bounds. You could do that, but you don't have to. You just do this entirely in u. And so this is going to be 1/5, and then integral of u to the fourth is going to be u to the fifth over 5. Okay, and then that's going to go from negative 4 to negative 3. And so that's going to be 1/5. I'm going to do it like this. So pull the 1/5 out. And so it's going to have negative 3 to the fifth over 5 minus negative 4 to the fifth over 5. And I don't know what those are going to be. So in fact, we can actually use Desmos to help us out. Of course, you use your graphing calculator as well, or scientific calculator. But this is often useful. So now one thing Desmos, like with your graphing calculator, make sure you put negatives in parentheses. So negative 3 to the fifth and negative 4 to the fifth. So 243 and 1024. So negative 243 over 5 minus negative 1024 over 5. And, oops, that's a minus a negative. We get plus, and so let's also do that on Desmos. So it's going to be 1/5. It's going to be, this is also going to be over 5. So negative 243 plus 1024. Let's do that. And let's go use Desmos or a calculator. We don't need to try to do that in our heads. So 1024 minus 243 is going to be 781. positive 781. So it's going to be positive 781 over 25. That probably, it's not going to reduce, we know, because 25 is just 5 times 5. So that's our final answer. Okay. So that's the substitution method using bounds. All right, let's take a look at one more of those. And let me decide which ones I have chosen, which ones I want to do. Okay, let's do, I think, call this number 2. So let's do this, the integral from, I believe that's pi over 4 to pi, what I've written down. And then we have cosine of x over sine squared of x dx. Okay. Now, also we can write this, go ahead and write it a different way slightly here, pi over 4 pi. Okay. Of course, we have the cosine of x. And then remember what this means, sine squared. And let me go a little bit better. So remember, sine squared means it's a sine of x squared. So this is going to be the sine of x squared. And also, I'm going to put up here is negative 2 dx. Okay. Now, once again, can we use u substitution here? I'm also going to think about our method. And the method I'm showing you, I've stated, basically, we're doing the same thing here. So once again, is it something we can do? So the derivative of our inside function is basically sine of x. Its derivative is cosine of x. So that should be possible. So that's what we have out here. Okay. So we want to choose our u, and that's just going to be sine of x. So let u is be equal to sine of x, and then du is going to be cosine of x times dx. And the derivative of x is dx. And once again, that means that dx is going to be du over the cosine of x. Okay. Now let's think about our bounds. Okay. Now for the lower bound, in fact, let me write this out as lower and upper. Now, one thing can happen sometimes with the u substitution method is that sometimes changing it to u, your upper bound and it's possible for your lower bound in terms of u to be greater than the upper bound. If that's the case, that's okay. That can happen. Okay. So the lower one is x equals pi over 4. Okay. And basically, then if we do sine of pi over 4, remember, that's actually going to be the square root of 2 over 2. Okay, that's the lower bound. And the upper is pi, and that's going to be the sine of pi. And remember, the sine of pi is 0. So this is an example where it's going to happen. Okay, so now we're going to substitute everything in. And so we go from lower bound of square root of 2 over 2 to 0. Once again, that's upside down, and that's okay, right? That can happen sometimes when you do the u substitution, but still it's all right. And then this is going to be, I'll use it this version here, the cosine of x times u to the negative second. Then dx is now du over the cosine of x. Cosine of x cancels out. And we're left with an integral just in terms of u, which is what we want. Remember, that's what we have to have. That's what we want. We have to have that. If that's not what we have, if you have an x left somewhere, and first off, double check your work, but if an x still is left, then something is wrong. This is the case where you can't actually use u substitution. Okay, now let's integrate that. Okay, and so remember that we can, so this is going to be, we add 1 to our exponent, so u is going to be negative 2 plus 1 is negative 1 over negative 1, and integrate that between square root of 2 over 2 and 0. Okay, and so that's just going to be negative I'll pull the negative out front. So negative, and then that's going to be, I was going to write this over here as 1 over u. So negative 1 over u from 0 to the square root of 2 over 2. And oops, that's interesting. Well, that's something interesting to look at. Okay. So what happened? Let's take a look what happens. Well, if I do the upper bound, I have 1 over 0. Okay. That's going to be a problem. Then minus 1 over the square root of 2 over 2. And I'll clean this up a bit. Of course, I still have 1 over 0. And this will be minus 2 over the square root of 2. But of course, what's the problem? Well, the problem is that 1 over 0, this is undefined. Okay, that's undefined. And so obviously what that means is just it's obviously not defined. Okay. So this integral is actually undefined. Which can happen sometimes. So basically what it means, there's probably an asymptote in it somewhere, and it's causing it to be undefined. Okay. In fact, it might help actually to graph this. So let's go back and take a quick look. So this is cosine of x over sine squared of x. Let's take a look at Desmos and see what we get. Okay, so y is equal to cosine of x divided by sine of x squared. Okay, and then also said from pi over 2, pi over 4 to pi. So let's actually make some horizontal lines at x equals pi over 4 and x equals pi. And yes, you can see what happens right here. You know, vertical asymptote here at pi, and that's what's happening. So basically, this is going to essentially infinity in a negative way. Okay, but basically it's going to be undefined because it has a vertical asymptote that is going to infinity. So basically, it means we have kind of like an infinite amount of area under that curve, and so that's not going to work. That can happen occasionally. Okay, and also realize we change our bounds. That result would also be different by change it to instead of our upper bound instead of pi, maybe pi over 2, something like that, that make it different. So that can happen sometimes. But the main thing to get out of this is the use substitution method. Okay, so once again, we kind of look at this function, and if it's multiplied by kind of this inner function is multiplied by another function, which is its derivative, except for a constant, be off by a constant, then we can do this. Okay, just remember how to, then if it's a definite integral, put your bounds in terms of u. And of course, if it's indefinite integral, just integrate and substitute back into the original variable once you're completed. Right? And that's the substitution method. Thank you. Have a good day.